Welcome to the next part. In transformer analysis, we were discussing the fundamentals of transformer for the first year BTech program. We already covered the construction, working principle and the EMF equation of the transformer. Now moving ahead, we will start with the losses that are present in the transformer and their reasons. The different type of losses in a transformer are generally divided into two categories. One is the iron loss or the core loss. Second is the copper loss. So the losses which are present in the core of the transformer due to the production of flux in the core, that is known as the core losses. The copper losses are the losses which are due to the current which is flowing in the conductor. These conductors are made up of copper which is having a suitable resistance, and hence the copper loss is represented by I square R. So I square R losses are basically the copper losses, and iron or the core losses are the losses due to the hysteresis and eddy current effect in the core that we are going to see. So iron loss is occur due to the reversal of flux in the core. So we know that in the core there is a complete magnetization and the demagnetization of the core material. So we will be having a complete hysteresis loop which indicates the magnetization and the demagnetization of the magnetic material. These magnetic material are made up of ferromagnetic material whose permeability is very high. So the area under this curve will represent the losses which is known as hysteresis loss. And this iron loss is practically constant at all loads from no load condition to the full load condition. So iron loss can be treated as a constant loss or one-time loss which generally depends upon the supply voltage. So once the iron loss has been taken into account, then we can only have the copper losses which are basically the variable loss. Iron loss do not depend upon the load. It will be same from the no load to the full load condition. Again, these iron loss is divided into two categories. One is the hysteresis loss and second is the eddy current loss. So hysteresis loss which occur due to the alternating flux in the core. In the previous lecture, we have seen that the flux is basically a function of time t. So there is a complete magnetization and demagnetization effect due to the alternating flux in the core, which result in the hysteresis loss. And it also depends on the factors such as the hysteresis loop area, the core volume, and the frequency of the flux reversal. So all these factors will impact the hysteresis losses. Now talking about the eddy current loss, it occurs due to the flow of eddy current in the core. So in the core we know that there is the flux which is present in the core. And we also know that whenever there is a current there will be a flux, and vice versa, whenever there is a flux there will be a current. These currents are present in the core in the form of circulating currents which establish the eddy currents. So eddy currents are the circulating current which are present in the core due to the flux produced in the core. And hence these eddy current result in the losses in the core. And it depends on various factors, the eddy current loss. First, the lamination thickness, the frequency of the flux reversal, the maximum flux density, the core volume, the quality of the magnetic material. So we prefer the magnetic material to be high so that less current can be taken to establish the flux. Also, the magnetic material has to be, or the core material has to be laminated, and so that its area is basically increased. So eddy current losses can be reduced by decreasing the lamination thickness or adding silicon to steel. So when we are adding the silicon to the steel material, we are getting less eddy current losses. The second broad category of the losses classification, that is the copper loss, and this is a variable loss which basically depends upon the current. So current is dependent on the load. So when we are changing the load, increase or decrease, then the current is changing, hence the copper loss is also changing. Moreover, the power factor, that is cos phi, is also variable depending upon whether the load is inductive in nature or the load is capacitive in nature. So due to the resistances of the primary and the secondary winding, we will be having the copper losses. So copper losses is given by, since copper loss is also known as I square R losses, and we have the primary current I1 and the secondary current I2, and the resistance associated with the primary current is R1, resistance associated with secondary current is R2. So obviously the losses we will be adding from the primary part, that is I square R1, and I square R2 is the secondary losses. So the total copper losses is the summation of the losses in the primary winding and the secondary winding. And it also depends upon the load on the transformer. So we have seen that the current is changing with respect to the load. So obviously the load plays an important role in the copper losses. It is proportional to the square of the load current of kVA rating. So obviously we have seen that the copper loss is directly proportional to square of the load current. So if there is a small change in the load, the copper losses will increase tremendously. Now we will classify the ideal and the practical transformer. First we will understand what is ideal transformer, and then we will move to the practical transformer. So when we talk about the ideal transformer, all the losses will be zero. So the losses will not be present in the ideal transformer. And we have seen that the losses means either the core loss or the copper loss. So core loss will be zero and the copper loss also will be zero. If copper loss is zero, it means there is no resistance of the winding or no resistance of the flow of the current, and all the leakage flux will be also zero. It means that only there will be the main flux and leakage flux will not be present. Whereas if we take the losses into account, then we get the practical transformer. So winding will have some resistances and there will be some leakage flux also present in the core of the transformer. So ideal transformer, it is assumed that all the flux which is produced by the primary winding is linking the secondary winding. However, in practice, this cannot be realized. So only in case of ideal transformer, you will be not having the leakage flux, which is just an assumption. Moreover, the leakage flux representation phi L1, because it is produced in the primary winding and it does not link the secondary winding. So only the main flux is common between the primary winding and the secondary winding. But leakage flux which is produced in the primary winding will not link the secondary winding, and similarly the leakage flux which is produced by the secondary winding will not link the primary winding. It is only the mutual flux which is common between the primary and the secondary winding. Now, since the leakage flux is in phase with the current of the primary winding, it produces a self-induced EMF EL1 in the primary winding from the Faraday's law. Also, the leakage flux in the secondary winding due to the secondary current will produce self-induced EMF in the secondary winding EL2. These two induced EMF EL1 and EL2, which are caused because of the leakage flux phi L1, phi L2, it differ from the induced voltage E1 and E2. We have to note that the induced EMF in the winding is basically E1 in the primary winding, and in the secondary winding it is E2. Whatever the leakage flux is there through the air, that is represented by EL1 on the primary side and EL2 on the secondary side. So we should not take EL1 and E1 to be equal. The leakage flux which is generating the self-induced EMF in the respective winding can be treated as the losses, and these leakage flux are equivalent to inductive coils connected in series with the respective winding. So we will be taking two inductive coils which are connected in series with the primary winding and the secondary winding of the transformer to represent the induced EMF EL1 and the induced EMF EL2. So EL1 is nothing but the primary current I1 multiplied with the reactance X1. This is the leakage reactance. So EL2 is given by I2 into X2, where I2 is the secondary current and X2 is the leakage reactance of the secondary side. Now, if we see in terms of the equivalent circuit for a physical transformer, so when you are supplying an alternating voltage here, which is represented by V1, then the current I1 starts flowing in the primary winding. This current produces a flux phi, which is known as the mutual flux, and which is present in the core of the transformer, and it links with the secondary winding. There is some leakage flux phi L1 that is flowing through the air of the core, which is not entirely present in the core, but it is flowing in the air. That is the leakage flux. So phi L1 and phi L2 are the leakage flux in the primary and the secondary winding due to the current I1 and the current I2. It is only the mutual flux phi which is common between the primary and the secondary current. And when the load is connected on the secondary side, then the current I2 will start flowing and there will be a voltage V2 across the load. The E1 and E2 are the induced EMF in the primary coil and the secondary coil. Now, if we take the transformer to be ideal in nature, so this is the ideal transformer. The ideal transformer will not have any losses, and it is represented by two coils and two lines which represent the core of the transformer. So here the induced EMF is E1 and on the primary side, and on the secondary side the induced EMF is E2. All the losses we are taking away from the ideal transformer. So it is not a part of the ideal transformer. So the losses, now we will be taking the copper loss in the primary side represented with R1. Copper loss on the secondary side is represented with R2. X1 and X2 represent the leakage flux losses, and there will be mutual induction M between the primary winding and the secondary winding linking through the core. The V1 and I1 are the voltages of the supply side, that is the primary winding. V2 and I2 are the secondary voltage and the secondary current. Note here that V1 will be equal to E1 only in case where the losses are neglected. Moreover, E2 will be equal to V2 only the cases when the losses are neglected. Also note that we have not taken the core loss into account in this equivalent circuit. The core loss will be taken afterwards by adding certain part in the equivalent circuit of the transformer. So let us see, when there is no load on the transformer, how the phasor diagram of the current and voltage are there. So if there is no load, it means that the core loss and copper loss in the primary winding will be there, because the current in the secondary winding will be zero. Because of no load condition, it is open circuit. So under open circuit condition, you will be not having the secondary current. So only the core loss will be there and copper loss will be there, and that too in the primary winding. Now the primary current I1 will be equal to the no load component of the current I0. So I0 represent the no load current in the primary side. So I0, the no load current, will be supplying the core losses and very small copper loss in the primary winding. Since this I0 is basically 1 to 3% of the full load current I1. So when load we are putting and the full load current, we are getting 1 to 3% of the full load current, that is I0. So it is very less quantity. Hence the copper loss is very less in the primary winding under the no load condition. It is only the core loss which is present. Now I0 will have two different components. It means the purpose of the primary no load current is of two. first component of I naught is basically I mu, which is the magnetizing or the reactive component responsible for the production of the flux in the core. The second one is IW, which is the power or the active component. This is because of the core loss representation. So I can say that I naught vector, because it will be a vector quantity, is equal to summation of I mu plus IW. Both are vectors. So I mu, which is the magnetizing component, is setting the flux in the core, and we can say that it is in phase with the flux phi. Whereas IW, which is responsible for the power loss. So power loss, we know that it is represented by watt, and it is the resistive component. Hence, it will be in phase with the voltage V1. So note here, I mu, the magnetizing component, is in phase with flux, and IW, that is the working component or the core loss component, is in phase with V1. So here we can see that if we take the reference to be the flux, so flux we are taking the reference, hence we can say that I mu component of the no load current is in phase with phi, whereas IW component is in phase with V1. Also we know that E1 and E2, that is the induced EMF in the primary winding and secondary winding, is anti-phase with 180 degree with respect to V1. And we can say that the current I naught is the vector sum of I mu and IW. So I can write that I mu is the vector sum of I mu plus IW, whereas phi naught is the angle between. So we know that the power factor angle phi under the no load condition, so phi naught is the angle between the supply voltage V1 and the current I1. So here I1 is nothing but the no load current I naught. So we will be having the angle phi naught. I can resolve into two different components. So I mu is equal to I naught sine phi naught, and IW is I naught cos phi naught. If we find the magnitude of I naught, then I will get under root of I mu square plus IW square. We have to memorize this formula and remember this phasor diagram. Now, since I naught is very less as compared to I1, I1 is the full load primary current. Hence, we can say that the copper loss in the primary winding is negligible, and all the losses under the no load condition is basically the iron loss, which is given by V1 I naught cos phi naught. So this is the single phase AC power, which is equal to voltage multiplied with current multiplied with power factor. So V1 is the primary voltage, I naught is the primary current under no load condition, cos phi naught is the power factor under the no load condition. Now we will see under the load condition. What happened under the load condition? So when we put the load on the secondary side of the transformer, the current I2 will start flowing. Earlier it was 0. When load was not there, then we have taken the I2 to be 0. Now due to the load, the current I2 will start flowing. So what happened in the working principle of the transformer is, when these current I2 start flowing, then there is a flux phi2 produced because of the current I2. This phi2 is opposing the main flux phi. So we can see that the flux direction phi is in this direction, which is the main flux, and because of the current, the phi2 is produced, which is opposing the main flux. But this flux phi has to be constant in the core of the transformer. So the primary current I1 will increase in such a way that it will oppose and nullify the effect of phi2. So phi2 dash and phi2 will cancel out, and the total flux will remain constant in the core of the transformer. When I say constant, it doesn't mean that it is a DC. The constant means the RMS quantity. So we can say that it is phi m by root 2. So that is the constant quantity. So the secondary load effect does not change the main flux which is there in the core of the transformer, because the primary current will increase. So when the load will increase, then the current will I1 will increase and phi 2 dash and phi 2 will cancel out each other and the total flux phi will remain the same. So the additional current, so I can say that I2 dash is basically the additional current which I can add here to produce the primary effect. Hence, we can say that N2 by N1, which was equal to I1 by I2 in terms of the transformation ratio K. Now the current I1, which was I0. Now in the previous discussion, we have seen that the primary current under no load effect is I0. Now once we put this load on the transformer, then I1 will increase and that increase will be represented with I2 dash. This I2 dash, we can say that this I2 dash is nothing but the transformation ratio K times the current I2 under the full load condition. So the two equations that we can remember is the primary current I1 is equal to no load current I0 plus I2 dash, and I2 dash, which is the extra current due to the load in the primary side, is equal to K times I2. And this we can do because the I0 is very less quantity. So I can say I0 plus I2 dash is equal to I2 dash. So in terms of the circuit, if the current I1 here in the first loop is flowing and we want to write the KVL equation in the first loop. Similarly, the current I2 which is flowing in the second loop, we can write the KVL equation in the second loop. So the first equation, that is the KVL equation or the mesh equation in the first loop, what do we write? So the supply voltage is V1. So we have written V1. All the losses here will be added up. So it is I1 R1 plus I1 X1. Note these are vectors. So I can write R1 plus J times X1 multiplied with the current I1 to represent the losses. Now it will be it plus E1. Now note here, we have seen in the vector that V1 and E1 was anti-phase with each other. Hence we have given a negative sign to include the direction of the KVL equation in the first loop. Similarly, the KVL equation in the second loop we can write E2. Now here the drop that will be present is basically I2 multiplied with R2 plus J times X2, which will be equal to E2 plus the total drop plus the secondary voltage V2. And as usual, the total primary current I1 is equal to I0, that is the no load component of current, plus I2 dash extra current. And this I2 dash we can write as K times I2. Now the load can be resistive, inductive and capacitive in nature. So either the load can be resistive or inductive or capacitive, or maybe the combination of RL and RC. So first we will see what is a resistive load phasor diagram. We have taken the transformation ratio K equal to 1. It means the number of turns in the secondary winding is equal to number of turns in the primary winding. And since it is a resistive load, obviously the voltage angle V2 and I2 will be equal to 0. So phi 2 will be equal to 0. Now if we draw the phasor diagram, so I have taken the reference as phi here on the x-axis, and we can say that the V2 and I2 will be in phase with each other because there will be no phase difference. And these losses I2 R2 and I2 X2, which is on the secondary side of the transformer, I2 R2 will be in phase with I2 and I2 X2 will be at 90 degree because it represents the inductive load. And we can write the KVL equation in the second loop to get the value of E2. And E2 will be the vector sum of, so when the secondary side we have already written the equation that E2 is equal to V2 plus I2 and it is equal to the drop R2 plus J times X2. So this drop we have taken here and we have added that with V2. So we are getting E2. E2 will be equal to E1 because we have taken the transformation ratio equal to 1 and E2 equal to E1. Obviously, we can see that we can have minus E1, which is anti-phase with E1. We are taking this side in order to take the KVL equation in the primary loop. So in the primary loop, we have seen that the KVL equation is V1 is equal to minus of E1 plus I1 and the drop that is equal to R1 plus J time X1. So here I1 R1 and I1 X1 represent the losses in the primary loop, and hence we are getting the voltage V1. The current I1 and the voltage V1, the net angle difference will be phi1. So phi1 is the power factor angle between the voltage V1 and the current I1, and the phi naught is the angle between the voltage V1 and the no load component of the current I naught. So here we have the no load component of the current I naught and the voltage V1, that angle is nothing but phi naught. And we also know that the current I1 is vector is equal to I naught, no load component of the current, plus I2 dash, which is equal to K times I2. So if I2 is flowing in this direction, the I2 dash will be anti-phase with each other, and I1 will be the vector sum of I naught plus I2 dash. So this will be your I1 current flowing. So the same phasor diagram we can draw for the inductive load under the condition that transformation ratio equal to 1. Here phi2 will not be equal to 0. There will be certain phi2 present in the angle between the voltage V2 and the current I2 because of the inductive load. So angle between V2 and I2 will be given by phi2. Here there was no phasor difference between V2 and I2. And hence we can write the KVL equation in the secondary loop here. And when we are taking minus E1, so this represent the KVL equation in the primary loop. And here we are having the no load component of the current and I1, which is the summation of I0 plus I2 dash, and I2 dash is anti-phase with I2. So whatever I2 we are getting, that will be anti-phase with this one. So hence we will be getting the phasor diagram of the inductive load. The same effect we can do for the capacitive load, where the current I2 is leading V2 by the angle phi2. So whatever we have done in the inductive load that is lagging in nature, here the current I2 will be leading the voltage V. So here we will be having phi2 angle, and this one we will be getting the KVL equation in the secondary loop. This one we will be getting the KVL equation in the primary loop. And minus E1 we are taking into account. So here E1 is this side to take the KVL equation in the primary loop. The I1 is again the vector sum of I0 plus I2 dash, and I2 dash will be anti-phase with I2. So we will be having phi naught as a phase angle between the voltage V1 and I0. Phi 1 will be the phase angle between V1 and I1, and there will be phi 2, that is the phase angle between V2 and I2. So these are the different power factor angle between the voltages and the current. So once we know the phasor diagram and the KVL equation, we can draw the phasor diagram and write down the different losses, find out the efficiency of the transformer that we have seen in the next lecture. So thank you for now. See you in the next lecture.